Hello, my name is Emma Mazzola. I am a senior at Meredith College majoring in math, and today I'm going to be talking a little bit about my honors thesis that I was working on with my advisor, Dr. Hunt. And we looked at some applications of elliptic curves and post-quantum cryptography. My goal by the end of this is to have everyone knowing what those words mean. So if you don't right now, don't worry about it. You're not supposed to. Okay. There we go. What is cryptology? We're going to start there, give a quick background. So cryptology is the study of encoding and decoding information. We're going to be looking at public key cryptography. So that consists of a method that utilizes two keys, one that's public, so everyone can view it, and one that's private, so only the recipient, the person who's meant to get the message, has that private key. The public key encodes information and the private key decodes it. So somebody encrypts information with a key, sends it, and then that person decrypts it with a different key. So some quick terminology, just to have you familiar for when I talk about it. It helps when talking about methods of cryptography to talk about Alice, Bob, and Eve. So typically Alice is the one sending the message, Bob is the one receiving it, and then Eve is the eavesdropper. So she's trying to get in the middle. She's trying to intercept the message and figure it out without that private key that Bob has. So her job is pretty hard because she doesn't have the key, and it's mathematicians' jobs to make sure that it's really hard for Eve because she's not meant to have it. Okay. Now we're going to talk about an elliptic curve. What is that? And then I'll talk about how it applies to cryptography. So an elliptic curve is the set of solutions to a Weierstrass equation, which is an equation of the form y squared equals x cubed plus ax plus b, together with a point at infinity, where the constants a and b must satisfy 4a cubed plus 27b squared equals 0. What does all that mean? So everyone, no matter your math background, should be familiar with y equals mx plus b. That's a linear equation. This is just another kind of equation with a different looking curve. That's all that this is. And when we take all of the sets on all of the coordinates on our curve, all of the points, we can put it into a set, and we have a set of ordered pairs. So, and I included an example as well, just so you can see what that looks like. So in elliptic curve cryptography, it's an approach where we rely on algebraic properties of elliptic curves over finite fields. So a finite field is just, think of it as something that instead of where we have an infinite graph that keeps going into space, it's finite. So it ends at a certain point and our numbers sort of loop back around in a way. So it doesn't look how you'd expect it. On the left, I added another curve, how you'd expect it to look. And that same curve is on the right as well, but it's just showing up as points because it's not going to be a continuous curve. We're just using whole numbers and we just have points. And we do that because now our set of ordered pairs is a special kind of set called a group, and it has algebraic properties that we utilize in cryptography. Okay, now switching gears, I'm going to talk really quickly about quantum cryptography. So quantum key distribution is a model developed in 1984, and I included a visual so that hopefully my explanation is making sense. You can follow along with the visual. So Alice is going to send a message in the form of photons, which are light particles, and she sends that across a fiber optic cable. And if you're familiar with binary, these we have different polarized states for these photons, and two of the polarized states each represent one binary bit, either 1 or 0. If you're familiar with binary, that might make a little bit of sense, and if not, don't worry about it. Just know that Alice is going to send those photons, and once they are on that fiber optic cable, before they reach Bob, they're going to go through a polarizer to change their state of vibration, and that happens randomly. And then Bob receives them, and he has to read them, and he has 2 beam splitters to do so. So each beam splitter reads for a different polarization. So one reads for a horizontal and a vertical polarization, as you can see in the picture, and then one reads for either 45 degrees in either direction. Bob doesn't know what the polarization is, so he just has to guess. So he just guesses and uses whichever beam splitter. And then he communicates back with Alice, and Alice is able to tell him which points he read, or which photons, he read using the wrong beam splitter. Those get discarded, and then the remaining is their shared key. So that's how the model works. And quantum cryptography is very, very, very secure for a few reasons. So we have these properties of quantum mechanics that make it very secure. So particles can exist in more than one place or state at a time. A quantum property cannot be observed without changing or disturbing it, and whole particles cannot be copied. So that means that Eve can't really eavesdrop, because if Eve tries to observe the system, she's going to disturb it, and that alerts Alice and Bob immediately. So they know that the system's compromised immediately. So in theory, it is unhackable. It is like you can't. That's the theory anyway. Now, post-quantum cryptography is, it's also called quantum-resistant cryptography. So it consists of the development of cryptologic systems that are secure against both quantum and classical computers. So right now, all of our methods that are standardized are sufficient against classical computer attacks, but quantum computers, not at all. Almost all can be hacked by a quantum computer. And engineers predict that sufficiently large quantum computers could be built within the next 20 years. So right now we don't have ones large enough to have this be a threat at the moment, but we need to be developing new methods that are quantum resistant so that when that point comes, we have methods that we can use to protect information. So I decided that I wanted to find a current method that used elliptic curves, but that was meant to be quantum resistant. I wanted to find the one that was being developed or had been developed, and I did. And so I'm going to briefly explain part of the process in a way that should make sense. I'm going to first go over the public parameters, so information that's public to anyone. Then I'm going to go over what Alice does, what Bob does, and what they do together at the end. So we start with our public parameters. It's an elliptic curve. It's a supersingular elliptic curve, which is just a special kind of elliptic curve, but they call it E0 or E sub 0. And then base points that are on E sub 0. So they're just points on the curve. We have PA, QA, and then PB, QB. Okay, so Alice is going to choose 2 random elements from a specific set. So she generates a set using some of those public parameters, one of those pairs of base points. And then from that set, she picks 2 random elements. And then she computes a specific kind of mapping called an isogeny. So a mapping is just something that takes one set to another. So we would put all of the points on our elliptic curve E0 into a function, and then out comes a whole other set of points, and that's a different elliptic curve. So Alice does this, and hers maps to E sub A. That's what they call it. And then she computes the points on E sub A that correspond to some of those base points that were public parameters that everyone can see. So she finds the ones on her new curve that correspond to those, and she sends them to Bob along with the curve E sub A. Then Bob does almost the same thing. So he also generates a set using some of the public parameters. He picks 2 random elements and uses them to compute his isogeny, which goes from E sub 0, the public curve, to E sub B. That's his new one. Then he computes the points on E sub B that correspond to some of the base points. And then he sends those points to Alice along with E sub B. And now here's where it all comes together. So now they both compute another isogeny, so another kind of mapping, using the information that they received from each other. And Alice's is going to map from E sub B, the curve that Bob sent her, to E sub AB. And Bob's is going to map from E sub A, the one Alice sent him, to E sub BA. And they are isomorphic, which just means that they're equivalent in some way, or it's a little bit beyond the scope of the presentation, but they're isomorphic. So when we calculate this value called the J invariant, we're going to get the same number for both of these curves, and that becomes their shared key. And that's just because of all of the math all that in between math and all of the requirements on the way that they calculated their sets and the way that they did the math, and it's just algebraic properties all working together. So that's really cool. And then the next step was for me to try and figure out how to go through this process with my own numerical example, and ended up running into something different. And that's where we spent the remainder of our time with the research up to this point. So we found an additional form for an elliptic curve, and we found it to be called the generalized Weierstrass equation. And it's y squared plus a1xy plus a3y equals x cubed plus a2x squared plus a4x plus a6. And that sounds like a mouthful. But here again, we have x and y are our variables, and then our a's are all just constant. So they're just regular numbers. And I have an example below, so you can see what it looks like, and you can see it's just another elliptic curve. So now what we ended up spending our time doing was trying to figure out how to convert this to the Weierstrass equation that we were familiar with, because we needed to be able to do calculations using that equation. So I went to the library. I took a trip to the library and checked out not one but 2 books for the first time in my 4 years at Meredith College. And I checked out some textbooks on elliptic curve cryptography, and I went through and figured out how to do these conversions. So we convert to another form in between, and then we convert to the Weierstrass form that we needed to get to. And you don't have to understand the algebra. I just wanted to throw it up there so that you can see it. It's just a lot of numbers and multiplying and substituting and expanding, all that jazz. And then we were able to put numbers into our example, into our like generic equations, and we were able to see this on a graph. And we found, as you can see, they're not the exact same curve, but they're equivalent in some way. And so in further research, we would love to continue to study exactly what this means and exactly what algebraic properties we can use between the two, and how to use them in the context that we're looking at. But yeah, so this is where we got with the research. It was very fun. I very much enjoyed working with Dr. Hans. I think she enjoyed working with me as well. And I hope you learned something new. I hope you enjoyed the presentation. And here are my references.